and then broke all of them, slept through everything else.
Woo! Strength and materials class. Yeah.
You're talking trash about me again? Oh, man.
No, we were just talking about how much we missed you on Wednesday, or on Monday.
Did you hear what happened?
Today's Wednesday, right?
Did you hear what
Don't
happened
even
to
get
me?
me started, I'm a mess. What's that?
So I got done with fluids in the morning, and I was feeling pretty sick. So I went back, got out of my bed, set my alarm for 10:50 p.m. on accident, and I
You sleep
slept
until 10:50 p.m.?
all the way until like 2:45, and then by that time I couldn't make it to class on time because I had to get a shower.
Too late that you could have easily.
I didn't want to
done
grace
that
you,
shower,
you guys were my stinky presents.
Could have taken.
How much do you sweat while you
5
sleep?
minute shower.
I don't think it was pre-nap stinkiness.
Is that on film?
Yes.
Yes.
If you hadn't handled that with your hands, I might have tempted to steal that cookie. I don't know where your hands have been.
Yeah, we don't know that it's in penis.
Yeah. All right, Blake is apparently not joining us because he's walking down there.
See,
it's
Blake?
like his antenna testing.
Yeah.
Close the door. Make him feel bad when he walks in.
Never mind.
All right.
Make him feel bad when he walks in.
Okay, this is it. This is it. Today's it.
Wait, it's the last day of
On
class?
Friday, we review for the final. We're skipping Buckland.
But we're officially
Love it.
reviewing.
But we are officially
I
reviewing.
like that.
Okay, so we'll go back over, kind of a little refresh. All right, so one thing I want to teach you before we jump into the problems today. So I don't think we're going to get to those example problems, which means the last three, whoa.
Oh, no.
Well, the last three homework problems will be discounted from the homework assignment. Because I don't think we're going to get to example problems covering what I'm going to talk about today. So, what that means is there's 10 points in those last three problems. So instead of assuming that there's 32 points on the homework, I'll assume there's 22 points on the homework. So you have to get 14 done to get the 60%. Everybody makes sense? That makes sense to everybody who's not eating in a race?
Does that mean you're done then?
All right.
Wow.
All right.
Huh?
You brought two things.
So, but if you've already done, as Clayton has, one of the last three problems, you'll still get credit for it. So I'll still count it total 14.
I think I would like that.
Okay? All right. So, you brought a book.
We all brought books today.
Really?
We're good
Wait,
students
Colin,
today.
where's your book?
Right here.
Dude.
We have a slow learning curve.
No,
about the
no
last
name,
class.
because it's mine.
You already have
I'm
one.
not sure where.
You don't need two.
No fair.
Juniors in the
Where? The conference room?
yeah.
The room.
I don't think I looked at
There's been one sitting in there all year. I just kind of borrow it when I need the tables.
Seriously?
Yeah. Why did I find this?
No, if it's not yours, I don't know whose it is.
That's
Okay.
That set you back like $3, Blake.
Let's move on. So, one last thing. If you remember the problem we had last time, 1222, we had this cantilevered beam with a variable.
Blake, you said you don't have to do the homework. That's
Assuming
what he said.
22 points.
Okay, we had this. Remember that from last time? Just do 14 points. Okay?
You ruined it. Tom was trying to convince me we didn't have to do it at all.
So, so now what happens, pray tell, if I should add an additional constraint there? Okay. So let's add the additional constraint there and see what happens. So we know this is 3 kips, right? Here at the end, 3 kips per foot. Right, and the whole thing is 9 feet long. But now I've added an additional thing at the end. How would you go about solving this? Someone? Anyone?
We'd have to start with free body diagram.
You go the same way that we have it, go to the long way.
Okay, so let's go with the free body diagram first.
Okay.
Right? So I put up a free body diagram. What, well, I can put this force on there. What reaction forces do I have? One at the roller. Call that B. What else?
Reaction force and reaction moment.
Reaction force, call that A. And reaction moment, call that M.
Technically, I have force in the x direction.
And technically I'd have a force in the x direction as well. A sub x, this would be A sub y. Okay. How many unknowns?
Technically 4. Realistically.
Okay. Technically 4. How many equations, equilibrium equations? If I've got 4 unknowns, how many equilibrium
realistic.
equations? Technically, not realistic.
Oh, technically.
Baseball. Okay. How, you said technically 4 unknowns.
Four.
Technically, how many equilibrium equations? No. I do not have 4 equilibrium equations. I have 3 equilibrium equations. What are my 3 equilibrium equations?
And
Some of the forces, some of the moments equal 0, some of the forces in the x equal 0, some of the forces in the y equal 0. So when you said realistically I have 3 unknowns, it's because you are already applying this to recognize that AX has to be equal to 0. But in doing so, you reduce my number of equilibrium equations to 2. 3 unknowns, 2 equations. What do we say?
Flex this up.
Go to the next problem.
What is this problem?
That's what they said.
What kind of a problem is this? If I have 3 unknowns,
Indeterminate.
it's indeterminate, right? So I have an indeterminate. If only I can spell indeterminate. Indeterminate equation. So it's an indeterminate equation, right? And it's indeterminate to the first degree because there's 1 unknown. If it's the second degree indeterminacy, then it means there's 2 unknowns. If it's the third degree indeterminacy, it's 3 unknowns. Okay, we have a first degree indeterminacy, right? Because we have 1 unknown that we can't solve for. 1 redundant unknown. Does that make sense to everybody? Okay. Just like we did when we talked about this problem. Remember that problem? And we had 2 unknowns, but only 1 equation, because this is, there's only 1 equilibrium equation, an x equation. And we had 2 unknowns, reactions at both ends. Or, when we had, I'm gonna have to draw this in 3 dimensions now. Right, where we had, and this is just at a wall. Right, so we had reactions. You guys remember this now? Right? And so we had, we were just solving a problem, you and I were just talking about a problem like this. Torsional problem. Right, and there was like a, the one I think we were talking about had, there was some kind of a fixture at the end with slots. You guys remember this from the homework? And we said, the screws in the end could move by 0.03 radians or something like this. You guys remember this from homework? Anyway, the point is, again, there's an indeterminacy. Because we don't know, I'm trying to remember on that, okay, I think this end was fixed. I'm sorry, this is my towel. This end, this is my applied torque. This end was fixed. right, with some kind of a rigid mounted end, okay? So these things all represent very, well, in this case, all of them, I think, are first degree indeterminacies. Okay. This one involves a normal force, this one involves a torque, right, a twist, and this one involves a shear force, or more precisely in terms of what we're doing, a bend. Okay, so we have an indeterminacy in normal, we have an indeterminacy in torque or twist, and we have an indeterminacy right in there. Huh. I've never had that happen. And here we have an indeterminacy in bending. Okay. In each case, we use material properties. Right here, we use the fact that we knew the displacements at the end were zero. Right? I mean, then the total, so the total strain of this end relative to that end was zero. We added the strains. And here, we added the twists. Right? We knew that this end was fixed, that end's fixed, then the total twist was limited. So we looked at the boundary conditions or the constraints of twist. Here, we're going to do the same thing. We're going to, again, use the constraint to solve the problem.
Woo! Woo! Man, I was in the last
Okay.
like that.
So, what would our elastic curve look like for this? Try again?
Parabolic.
It would not be parabolic.
Kind of be like a little bit and a bit more.
What would it look like on the left end?
Kind of slowly sinking.
At the very left end, it would not be slow sinking.
Zero. Oh, okay, zero.
Right, it'd be a slope of zero. So it has to come straight out at this end and then dip up. Right?
Isn't the dip centered more towards the right side?
Yeah.
Maybe it is.
Yes.
Now, we don't know necessarily where the dip is centered, but the point is, the left-hand end we know is straight. Right? And the right-hand end we know has no deflection. So in this case, we now can't solve for AY like we could last time. And last time we knew what AY was. Right? Because we knew it was the only reaction force that had to equal the total downward force. But now we have a distribution between AY and B. So now the moment at some point along here, so now we do a section analysis. We have AY pushing up here. Let's call it A. There's no X. We have A pushing up here. We have the ramp pushing down here. So then we have V here and M here. Right? That's what we had. Right? But now, instead of having a number for A, we have an unknown for A. So our moment expression, I think I got it from last time. What was our moment expression? Right, it was 3 over 9 times X times, give me the whole expression again.
13.5 x minus x cubed over 81. That's supposed to be 18, I think, minus 81.
Minus 81? Yep. And now instead of 13.5, we have AX, or A. Right, the reaction force at A. So we have an additional unknown. Then we go through and we do the next step. So E, I, dV dx, the integral of this, right? So we'd end up with AX squared over 2 plus x to the 4th, or minus x to the 4th over 72 minus 81x, right? Whereas last time we had 13.5 here, divided by 2, now we have A. You follow the process? Right? And then we get to the other thing, the other one. What was our EIV? So EIV was equal to, now it's going to be A over 6 x cubed, right?
Minus, yeah, x to the 5th over 360 minus 40.5 x squared minus c1 times x plus c2.
there's our expression now. Okay. So now, all we've done is in order to remove our indeterminacy, we've incorporated one of our unknowns, one of our redundant unknowns, into the expression. But now we have to have 3 constraints to use to solve this. Right? Remember last time we had to have 2 constraints? What were the 2 constraints we used last time? Everybody remember? Without the roller on there, what were the 2 constraints?
The slope was 0 at x equals 0.
All right, this was equal to 0 at x equals 0. So we got C1 equals 0, which is still true.
And then v of x at 0. So v of 0 equals 0.
This one equals 0, because the displacement at that point is 0. So C2 is equal to 0, which is still the case. But now we have to have a 3rd constraint. What's our 3rd constraint?
v of x at x equals 9.
Right. It's the thing that we added that is our now redundant or indeterminate constraint. So by adding the indeterminate constraint out here, we've added another constraint in the equations. And that is that at x equals 9, v equals 0 as well. So this bottom equation, I said equal to 0 at x equals 9. And then I can solve for a. So we use the same beam deflection process we've been working on to also solve for indeterminacy. And if we had an additional constraint, let's say I put another roller in the middle, right? I would now have an additional unknown, that would be a C, pushing up here, but I would have an additional constraint to use to find this. Does that make sense to everybody?
We
So-
only have 2 equations.
Yeah, I'd have these 2 equations, but I would have, so it would, which would involve an A and a C, or actually in this case, by putting additional constraint in the center here, I would actually have 2, you know, I would have to do an equation, you know, an X coming in from this end or something, right? Because I have to break the equation in the center. You know what I'm talking about?
Right.
So, but the point is, I would still end up with equations. I would still know my C1s and C2s from the other constraints, and then I would be able to interpret my A and C in this case. It increases complexity. The more constraint I put in, the more complexity. But for every constraint I add a constraint that helps me solve for yet another variable down here. Okay, does that make sense? Okay, so the point is we covered the other 2 kinds of indeterminacy. I just want to show you that we would use the same beam deflection as well to determine indeterminacy, to solve indeterminacy in the 3rd orientation. Normal force, twisting force, now bending, or shear force. Okay, does that make sense to everybody? Okay. Having explained all that, I don't think we're probably going to get to those problems. We're just going to go ahead with the problems that we have. But I understand you've hopefully got a handle on those, and maybe, let's maybe come back to that one actually. Let's do 1287. Let's do 1287, and then we'll come back to 25 if we need to. Okay? So here we have 1287. We have a W12 by 45. And general shape pinned at one end and rolled at the other. We have a 12 kip load applied at the midpoint. And we have a moment externally applied here at the end of 50 kip feet. And these are A, B, and C. Okay. W1245, made of A36 steel. Subjected to that loading, determine the deflection at its center C. So what are we going to do?
Pretty bad.
Free body diagram, all right, the free body diagram. 12 kips there. What else do we have?
Reaction forces. Y.
A, and B. We actually have the 50 kip feet out here. Okay? What do we do now?
We can do our final reactions.
Okay. So anyone find the reactions?
You already know the reactions, right?
Do we know?
Well, it's the force is applied in the middle, so we know that A and B are just both 6.
No.
This is the moment, but
Yeah, there's an additional moment. What?
if you were to do summation of forces in
Well,
Y,
you can do the moment and
I say we sell moments about B. What about?
I'm going to listen to Kayla on this. Okay, so that doesn't get us A or B. And Kayla suggested we do moments about A, and somebody over here suggested moments about B. I'm going to suggest we go with moments about A. Okay, just because the way it's drawn, it makes it a little more conceptually simple.
Okay, because then you don't have to add in the 50 kip moment.
No, I still have to add in the 50 kip moment because it's an applied moment, no matter where it is.
Oh, okay.
So, do we even need to do the reaction forces for this?
Can we use appendix C?
Okay. So, it's two different questions. First of all, do we need to do the reaction forces? Why would we not need to do the reaction forces?
Well, if we are using appendix C.
So you're both saying the same thing?
Yes.
Okay, yes. So, we could indeed just go right to appendix C. Right? So look at appendix C, because this is a simple beam, right? Simply supported beam.
That's the first one.
So if you look down a simply supported beam, you have a variety of different loading configurations. Is this a loading configuration that's shown in the simply supported beam?
Yeah.
Which one?
The very first one.
No, it's not the first one.
It's a combination.
it's a combination.
It's a combination of which two?
First and the third one.
It's a combination of the first and the third. See that? So in fact, we don't really have to go through the whole process, free body diagram and all that kind of stuff. We could skip to the end. Skip to the end. Nobody? Nobody?
Skip to Malu.
My darling.
Smoke them out.
You guys need to expand your horizons in terms of classical film. Skip to the end. I'll give you a I'll give you a hint.
Sing us a song, sing us a song.
I'll tell you who said those words. Prince Humperdinck.
Humperdinck, I know that.
Yeah, it's the
I-
Princess Bride.
It's
Like,
always
you don't know it.
If you don't know, guess Princess Bride.
Oh,
That's very
okay,
true. It's
okay,
such a
okay.
red card.
It's the what?
Well,
The Trump card and apples to apples.
Wow.
Humperdinck.
Yeah.
Or
Is
Helen
Humperdinck
Keller.
in,
Either one's pretty much.
Humperdinck.
is
Anyway.
Humperdinck in The Mockingjay? Or whatever that movie, Hunger Games?
No.
I'm not a witch.
Humperdinck.
No.
You're right. All right. Let's focus. Let's focus.
No.
I guess,
President
sorry,
Snow.
I guess then my
Go ahead.
I'm being calm today with questions, but I guess my next question would be, will we have an appendix C style?
I will make sure you have an appendix C style.
Okay, so it would be better for us to go this way then.
Right. So this is the better way to go.
Okay.
Okay? So, what do we have then from Appendix C that we can use in this situation?
We're looking for the deflection.
We're looking for the deflection.
Add the deflection.
So add the deflections. So what are the deflections?
This is negative PL cubed over 48 EI first.
Negative P L cubed over
48 EI.
48 EI.
And then we're gonna add that to, you have to use the elastic curve because we're not going for the max, we're going for the center. That one, right? There's two, it gives a V max, which is not in the center.
Yes, but we don't want, we want to know the elastic curve.
Right, but we wanna know in the center, not at the max, right?
Right, that's what I'm saying.
Yeah, so then it's negative M plus negative MO times X over 6 EIL times the quantity L squared minus X squared. And then
What was the denominator?
we, 6 EIL.
6
Yep.
EIL.
And then times the quantity L squared minus X squared,
So, did we miss that?
and then X is 2.
Yeah, one thing's missing.
The first part should have. Yeah, it should be the negative px over 48 EI times the quantity of 3L squared minus 4
No,
X squared, isn't
no,
Why?
because the max is at the middle.
Yeah.
it? Is it?
The max is at the middle.
Oh. Okay.
Okay.
That's,
Well, you wanna find it.
So they're saying
No,
you
yeah,
don't
no,
have to do the last
the-
figure
okay,
because the max is at
So,
the middle.
yeah,
The negative-
I'm gonna do, oh yeah, I'm gonna
Yeah,
get
go
that.
ahead.
So what goes in here?
3L squared minus 4X squared.
Okay. But we're looking at the center,
Mhm.
right? At the center, x equals L over 2.
Yeah.
So this becomes 3L squared minus L squared. That's 2L squared, which comes up here, is that right?
Yeah.
L over 2 squared is L squared over 4.
Goes back to what it-
Right, so it becomes 2L squared. So it should
Becomes,
become this thing, yeah.
oh,
L cubed, but I'm trying to figure out where, oh, because x equals L over 2. Right. So this becomes L cubed. So that we don't have to do that piece, because the first one is specifically evaluated at the center to begin with.
Yeah.
Right, so we can just plug in x equals L over 2. This L cancels that L, so we end up with equals minus PL cubed over 48 EI minus M0 4L squared, 3L squared times 3L squared over 24 EI, I think. I think that's what it comes down to. Because this becomes 3/4 L squared, and we have an extra half in here, so that's 112 times 3/4 is 3 over 24. No, 3 over 48. 3/4 L squared. Got a 4 in the denominator, got a 6 in the denominator, got 2 in the denominator. That's 48. Okay. So, I don't even know if they did that in here. Oh, yeah, look at that, they did. But they calculated it. Never mind, they actually plugged in numbers. I hate when they plug in numbers. So that's equal to minus 1 over 48 EI times P L cubed plus 3 M0.
Negative.
And put the factor of minus M. Okay. Is that good?
We lost the L,
Which L?
after
It's
M.
L cubed. Either-
Oh, L squared. Right. Okay. And then, if we plug in the numbers, and that should give us V at C. And according to them, that is 0.895. And it's negative, indicating it was a downward depression, which we all knew going in. Right? So it makes it a much easier process using the tables because we've already worked out a solution for this particular configuration. Okay? Yes?
Why do we choose to plug in L over 2 for X?
Because C occurs at x equals L over 2.
Okay.
Right, we're moving in from one end to the other, it doesn't really matter. But I think in the diagrams, they expect X to come from the pin. Yes, X comes from the pin. So in this case, X would be coming from this direction.
Okay.
Okay. So at x equals L over 2 is where C is.
And you just simplify it down, plug it in.
And I just plugged in x equals L over 2 to get to here, and then simplified it down to the bottom line.
Because we have no other X forces, does it really matter, like say in the book if it had this thing flipped with the moment at the pin and flipped around, does it really matter at all? So if like say, because in the book say a diagram had the moment where the pin's at and not where just the roller's at, would it technically?
So you had an applied moment at the other end?
Yeah, could we take it even, and then say in the homework we had this problem, could we technically still apply this simple loading? Because the difference between the train and a roller for this, for somebody stressed in the horizontal plane, vertical plane.
So this moment, if you look at the elastic curve expression, that where are we? Right here. So the minus m naught x over 6EIL times L squared minus x squared, right, is not symmetrical, right? That means that the deflection you get is not the same on the left end as it is on the right end. So applying a moment down here is not going to get me the same curve as is defined by this one.
Well, would it not though if we just flipped our x-axis?
Okay, but you've got, then, you mean run your x from the other end,
Yeah.
from this end. Yeah, so then that should be,
But I guess what I'm asking, the pin in the roller is not affecting this moment at all.
right, the pin in the roller is not affecting this moment. But you have to define, but everything is defined in these equations
Yeah.
with respect to a particular orientation of x.
Okay.
So if I switch my moment down to this end, then I've got to switch my x coming from the other end. Okay. All right. Any other questions? Okay. Then let's do the next one. We might actually get back to 65. Maybe. Okay. So now we have another simply supported beam. It carries a uniform load. Let's see, simply supported beam. Doesn't really look simply supported, but okay. I'm not sure I understand how they've got that defined as simply supported, but I think those are maybe supposed to be pins at both ends. Anyway, it carries a uniform load of 2 kips per foot. Code restrictions due to plaster ceilings. All right, so this is one of the things we were talking about. Why do we need to care about deflection? Because if it's got a plaster ceiling, then we can't, deflection will crack the plaster. So code restrictions due to plaster ceilings require the maximum deflection not to exceed 1/360th of the span length. Select the lightest weight A992 steel wide flange beam from appendix B that will satisfy this requirement and safely support the load. The allowable bending stress is given and the allowable shear stress is given. Assume A is a pin and B is a roller support. Oh, there it goes at the end. Okay. So A is a pin and B is a roller support. So what do you want to do?
So it says maximum deflection to not exceed 1/360th of the span length. That just means the 4 plus 8 plus 4 over 360 is what the deflection in here. Okay.
Right.
Just want to make sure I understood it. That's what I wanted to do first.
Okay. I'm gonna calculate the,
No, I wanted
Vmax.
to make sure I understood what it was asking.
Okay. So essentially what they're saying is, which is 16 divided by 30 inches. Right? Does that make sense? Right, 16 over 360 feet, 360th of a foot, so I gotta multiply that out of 12 in the denominator to get to inches. Okay? So,
But 16 needs to be divided by 12 as well, because 16
no,
feet.
no, it's 1/360th of 16 feet. So the maximum deflection is 16/360ths of a foot. So I have 1 foot in there. The numerator's foot, the denominator has no unit.
Just multiply by 12.
I just multiply. Exactly. Trust me, it's 16/30th of an inch, okay? Which is still half an inch in the middle, right? So the plaster's still bowing half an inch, but the point with the plaster is it has to be the relative bow. If I bow a half an inch on a 1 foot span, it's gonna crack the plaster. If I bow half an inch on a 16-foot span, it's not gonna crack the plaster. Okay. All right, so we've got that. What now? What do we do now?
Appendix C.
Appendix C? You're gonna go with Appendix C as well. Okay, well, I'm gonna draw a picture just so that we have it. And they said treat A as a pin and B as a roller. So I'm drawing it as a pin and a roller just so we keep our sanity. And this is 2 kip per foot. And then there are additionally loads applied here and here of 8 kip. And those distances are 4 feet from the ends with 8 feet in the center. Okay. So, can you use the table?
Yeah. 2 of the second one and 1 of the first one. Superimposition.
2 of the,
Second one, where the P is not at this very center.
okay.
Well, I guess, would those work, because we're constrained at both ends, aren't we? On this one? Oh, no, this one we're not, we have a roller at one end.
It does.
Okay, so we have this configuration. So we have 2 of these.
Right.
1 at A equals L over 4, and 1, right, A and B, those are the, yes. 1 at A equals L over 4, and 1 at B equals L over 4. So if you look at the expression you've got out there, they're defined in terms of B. Right, and this expression accounts only for loadings between 0 and A.
Right.
And so B is L over 4, then for the first one, B becomes 3L over 4, or you can flip it around. Okay, but, so what we end up with then,
But you gotta add the other one, which is the mass distributed.
right, the distributed mass. So what's the V for the distributed mass? Mass.
V is going to be minus WX over 24 EI times quantity X cubed minus 2.
Hold on. For the distributed loads,
Oh, V max. Okay, I'm sorry.
where's the maximum gonna occur for all of this?
In the center.
In the center, right? Because of the symmetrical loading of the 8 kip things, we are gonna end up with the central, the Vmax being at the center. So we only need to concern ourselves with the center. What's the center Vmax for the distributed load?
between minus 5 W L to the fourth over 384 EI.
Where W is,
W is 2, okay. Okay. What is the deflection caused by the individual loads?
negative P, okay, starting with the, I guess we'll do the left one first. The negative P, where B is equal to 12 feet times X over 6 EI.
Right.
No.
Hold on a second, what did you say? It was 3 B times A? Right, because P, so 3B is 3L over 4, 12.
Yes.
A is L over 4,
Oh, you're putting,
in terms of the total length.
okay.
Okay, and you'll see it in why I want to do that in a
There's
second.
no,
Okay.
there's no A reference though.
Yeah, there's.
That's it. A, B, yeah, but.
Oh, you're doing the elastic curve you're doing.
Wait, you wanna do the deflection though? You wanna do this one
B and A. Oh.
No, that's fine, that's fine. No, he's doing the right thing, he's doing the right thing.
Okay, but I was just reading you the elastic curve for the other one, and it was the wrong thing.
For which one?
For the distributed load.
Yeah, but it wasn't the wrong thing, but we know
That's
where
what-
X
Oh,
is
we
gonna
know
be.
where the max is.
Right, we know where the max is, we go right to the max.
It's the max.
But the max for this loading is going to occur here at X equals A. It is not going to occur back here at the center. So we can't use the max loading for that.
Okay.
Does that make sense?
Yep.
Okay. So what do I have? Sorry, B
So-
times X,
Yeah,
right? And X, where we're going to be concerned about, is L over 2,
yes.
right? Divided by what?
Divided by 6 EIL
Mm-hmm.
times L's, the quantity, L squared minus B squared, where B is L over 2, or L over 347, and minus X squared, where X is L over 2.
Okay. So that one is for yeah. Okay. B actually B's got to be L over 4.
Yeah.
Right, because these are only valid between the end and the point of application. Right, they're only valid for x's less than a.
So is this one for the left one or the right one?
So this is for the right one.
Mm-hmm.
B is this piece. A is the piece
Okay.
over here. So we have to plug in L over 4 for B.
And since P is symmetrical about the center, can't we just multiply that by 2?
Right. And so since the thing is symmetrical about the center, so in other words, that's how much this one's going to cause the center to deflect by itself. This one would also cause the center to deflect by the same amount. We would simply count our x in this direction, and B becomes this piece. You follow me?
I follow, I don't know if I believe.
So let's look at the elastic curves that each of those things would give me. The elastic curve for the piece on the right would look something like this. Exaggerated, right? The elastic curve for this one would be the symmetrical opposite of that. The deflection at the center is the same for both of them.
Yeah, but if you flip the way you're reading your x, doesn't that change your equation?
No, because if I flip the read for the second one, my x is coming in here.
Oh, because it's still
But
L over 2.
B is still L over 4 and still L over 2, so all that stuff stays the same.
Okay.
That's why I wanted to leave it in terms of L.
Mhm.
so that we can see coming in this direction, everything's the same.
Yeah.
So I essentially take that second nut equation and multiply it by 2. Take a 2 in there. Okay? And,
Oh,
yeah,
sorry.
go ahead.
I still think we have an error though.
What's
Because
that?
it says X has to be less than or equal to A.
Right, so A is here,
Oh, B, yeah,
X
sorry.
is here, so we're less than A.
Yeah, you define, okay, yeah, I got you.
Okay.
Because you have to redefine A and B when you go to the other side.
Yeah.
I thought we were doing it the other way, but yeah,
You
you're right.
good?
Yeah.
Okay. So what does that become? That becomes 5WL to the 4th over 384 EI plus 2 cancel that 2. So we end up with, and this is L to the 4th, so this is 1/16 L. So this is 15/16 minus 1/4 L, which is 4/16, so we have 11/16. So 11 over 6 times 4 times 16 times P L to the 4th over E I L. So let's just get rid of that L, make it a third. Does that look right? I don't know what 24 times 16 is off the top of my head. 64 times 6, 384. Woo-hoo! Sweet. 384. I love it when a plan comes together. All right. Does that make sense?
Princess Bride, right?
Okay.
Well, at least he's paying attention.
Hopefully it's not.
Okay. So, do I know E and I? Do I know W? Do I know L? I mean, what do I know? Do I know all my variables?
Okay, well, we will look them up for you in the appendix.
Okay, what's E? What's E? 29 what? 29 times 10 to the third what? Times 10 to the third KSI. Okay. Okay, we do everything in KIPS and KSI. What about I?
I see an appendix.
That's what we're trying to do.
Yeah, we're trying to define the lightest weight steel flange beam. We don't know what I is. Right, we have to find a steel flange beam that will meet these criteria.
So now we solve that because we know the max.
So we know Vmax, we can solve for I. Or, alternatively, we know sigma allowed is 24 KSI. Right? So, if we know the maximum moment, we can use S to solve for if we find the maximum moment, we can find our S. And use work backwards from the S. So we can find the maximum moment. How would we find the maximum moment? Take the second derivative of this expression with respect to, well, actually it wouldn't be this expression, it would have to be the actual elastic curve expression.
So, yeah, so we wouldn't have wanted to equate to B max, just want to find elastic.
Right. Or then we could actually go through here and solve for I, knowing that Vmax is constrained, and go back and look for the lightest weight I, the lightest weight white point beam that has that I.
If we're using that method, S equals Mx over sigma mod, isn't S I over C, or, yeah, S is also equal to I over C.
Right, but I and C both depend on which beam, which white point beam you choose.
So,
So we're not expressly, we're solving for the ratio of I and C, not for a particular I.
Okay.
so what's the difference between the two, like, studying equal to B max and solving for R and then or finding X? Like, is one way harder?
So, you have to meet both constraints. So if we would solve for an I, a particular I, this way, and then make sure that that beam, that I, also satisfies this transition, because that I would also have an S associated with it. And make sure that that also meets this criteria. You have to meet both criteria.
So you take the derivative twice, gives you the N.
Take the derivative twice, gives you the M. Or you can go back to the three-body diagram and do the M that way.
But you still have time in the equation. Like, if you take the derivative
Yeah,
twice.
but again, if we do the three-body diagram, solve for M this way, we get an S. That S, we look up in the table, comes with an I. And then we use that I to make sure our Vmax is not under half an inch. Or it is under 1637.
Hey, Chandler.
So you have to meet both criteria. You pick one, you solve for that one, and then you go back and make sure that it meets the other one. If it doesn't, then you have to go to a heavier beam.
Okay.
Okay? And there you have it. All right.
Blade.
So everybody means bluff